For number 16, we're going to first find the local maximum and minimum points, and then we're going to find the points of inflection. So you find the maxes and the mins with the first derivative. So we're going to take the first derivative. Here it is. I've already done all the algebra. And that gives us, when we set the first derivative equal to 0, there are no places where it's undefined. So the first derivative is 0 at negative 1 and 2. Those are the critical numbers, the first derivative. So critical number, and 2 is a critical number. Since these are our critical numbers, they are possible values where maximums and minimums can occur. However, they have to be tested. You have to test the values in the first derivative. So you have to look what's happening, because it's at 0, at negative 1, and at 2, but what's happening before? So if we look at a number and we put this number into the first derivative, say we look at the first derivative of something less than negative 1. So say we put f of negative 3 into the first derivative, so f prime of negative 3. So if you put negative 3 in here, you're going to have a negative and a negative, and two negatives make a positive. So that's going to give us positive values. Since the only place this can change is at negative 1, then that means it's positive all the way to infinity, and that means f of x is increasing. So this is increasing. So since the derivative is positive, that means the function is increasing. So now let's look between negative 1 and 2. So let's try f prime at 0 and see what the sign is there. So f prime at 0 gives you a negative number. So that means that all the way between here is going to be negative. And that means that if our derivative is negative, f of x is decreasing. And then we're going to look at a number that is, actually all the way up to 1. There's my critical number at 2. That is greater than 2, like maybe f prime at, 5, or just any large positive number greater than 2. So 5 plus 1, that gives you a positive. 5 minus 2 gives you a positive. So all of these signs are going to be positive because we tested it in the first derivative, and that means the original function from 2 on is going to be increasing. Yeah, and this one actually goes all the way to 2. Sorry about that. Okay, so that is our increasing and decreasing. So if we're increasing, then up here our function goes up and then comes back down. We have a max here. We have a maximum value because the derivative changed from positive to negative at that spot. And we have a minimum value here. And we can find those values by plugging it into the original answer. So to find what these values are, you would actually plug in f of negative 1 and find out what that equals. And then you'd also plug in f of 2 for the minimum and find out what that equals. So when we do the math, we get f, when you plug in negative 1, you get 12. So it has a maximum value of 12 at negative 1. And our minimum value is negative. So when you plug in 2, you get negative 15. So y has a minimum value of negative 15 at 2. So let's look at points of inflection is the next thing, in concavity. So right now we're looking at the second derivative. So the first derivative is the function increasing or decreasing? So is f of x increasing or decreasing? That's what you find out with the first derivative. And with the second derivative, you find out is f of x concave up or down? Up or down? So that's what we're finding out. So right now we have a possible inflection point at 1/2. Now I'm going to go ahead and put it on this graph up here because why not? It's right here at 1/2. So 1/2 is our possible inflection point. So that's our critical value for the second derivative. So 1/2 is going to be where the magic happens. So if we put 0 into the second derivative, so if we say f double prime of 0, we're going to get a negative number. And if we get a negative number, that means boom, boom, concave down. And that's awesome because that also proves our maximum. Because if you look, if something's concave down at a number, then you're going to have a maximum value there, and you do. So then let's look at a number greater than 1/2. Let's pick 1. So if you put 1 in here, 12. So if you look at f double prime of 1, you're going to get 12 minus 6, which is a positive number. So now we are concave up, and that is awesome because it verifies our minimum. And this also says, hey, there's an inflection point at x equals 1/2. And that is a point of inflection point. And that is POI, point of inflection. So the last thing we're supposed to do is we're supposed to sketch a graph. You don't define x-intercepts. This is just a sketch. So we're going to go ahead and put the numbers we know. First, we're going to put our critical numbers, and that's where they change from max to min. So at -1, we have a max up here at 12. We have an inflection point at 1/2. And then we have another extrema. So maxes and mins are called extrema at 2. Alrighty, so those are things where the magic happens. Now we're going to go ahead and plot these points for the function. So if we plug in 1, we get 12. So -1, positive 12. So let's just say 12 is up here. Boom. And we're going to say 2 is -15, which is down here at -15. And that was the minimum value. And the concavity changes at 1/2. Now this is a sketch, so I'm not going to get the y value for the point of concavity. We just know it changes there. Also note, this is a cubic function. So it's going to wiggle, wiggle, wiggle. It is positive 2x cubed, so it's going to, the end behavior is positive. That means it's going to, I don't know if you guys remember this from Algebra 2, but it's going to end up in the air like that. So if you work backward, that means it's going to start down here. So it's going to start here and go up. And that really makes sense with what we have. So, because this function, I'm going to draw it now. It's going to go all the way up, and it's concave down. So it's this shape right here. So it's going to go all the way up to here. We don't know where it comes from. And then it's going to swoop back down at about 1/2 somewhere. Concavity changes. And so there's an inflection point here, and it goes from concave down. And then all of a sudden, hey, we're concave up. And it continues on. So this is a sketch. We don't have to know these x values. Like, we don't care where the intercepts are. As it says it's not necessary to find the x-intercepts. So this is a general sketch from the function using increasing, decreasing, and concave up and concave down.